Similarly to how Nicholas Copernicus presented the heliocentric model, another dazzling correction of how we might interpret the universe could arise, starting a discussion known as the emergence of cosmology. This emergence is set apart by critical disparities in our estimations and comprehension of the universe's crucial properties, like its age, size, and pace of development. Neil deGrasse Tyson has noted that the discovery of the James Webb Space Telescope, JWST, has stopped this discussion with a picture that resists material science. So, what precisely is this emergency, and how does the James Webb Space Telescope contribute to it? Well, contributing to it is a bit of a misrepresentation. It's more similar to a survey that has been in progress. The emergency refers to a place where how we might interpret the universe is challenged, especially in terms of its age and size, which are connected by an extensive safety buffer. The presentation of the JWST has been pivotal in this setting. Before this advancement, we were limited in how far we could see into the early universe. However, with the JWST's further developed abilities, space experts can investigate considerably more distant worlds, giving us new viewpoints on the universe and testing a portion of our past conceptions. This advancement allows us to peer further back in time, closer to the Big Bang, and observe galaxies as they were forming, which provides critical information that can either support or challenge our current models of the universe. To understand the emergency in detail, looking into the view is significant. The standard model of cosmology, known as the hot inflationary Big Bang model or lambda cold dark matter lambda CDM model, has been exceptionally successful in making sense of various elements of the universe, from gravitational lensing to the structure of the cosmic web and the development of galaxies. The lambda CDM model suggests that the universe began with a Big Bang followed by a period of rapid expansion and has been expanding ever since. It includes components like dark matter, which applies gravitational forces, and dark energy, which drives the accelerated expansion of the universe. However, each groundbreaking observation, particularly with instruments as cutting-edge as the JWST, raises the possibility that our current model might be inadequate or need to be updated. The lambda CDM model makes explicit predictions about the attributes and behavior of galaxies at various stages of the universe's history. For example, it predicts that galaxies in the far-off past should be smaller, less evolved, and contain fewer heavy elements compared to those we see in the nearby universe. This is because heavier elements are formed in the centers of stars and distributed through processes like supernova explosions, which take time to occur. The description you give is about how the standard model of cosmology predicts the movements within groups and clusters of galaxies, as well as the properties of the cosmic microwave background, CMB, as we travel back into the past. According to this model, galaxies should be smaller, bluer, less evolved, and poorer in heavy elements at astronomical distances greater than our own. This would lead us to expect to enter times of the universe without apparent stars or galaxies. However, researchers have found contradictory evidence that challenges these expectations, resulting in an emergency in cosmology. The emergency in cosmology centers on the uncertainty about the age of the universe. Different estimation strategies give various outcomes, leading cosmologists to struggle to accommodate these disparities. To attempt to address this issue, researchers use several techniques to measure the age of the universe. One of them is the study of cosmic background radiation, which involves unraveling the history of the expansion of the universe and using mathematical models such as the Friedmann equations based on Einstein's theory of general relativity to determine the expansion rate and thus the age of the universe at different times. The CMB, a remnant radiation from the early days of the universe, is a key tool for this calculation. Detailed maps of the CMB, like those provided by the European Space Agency's Planck mission, offer important information about the composition of the universe. However, these maps lack data on dark energy, a significant component of the current universe. Despite this limitation, researchers can use the Friedmann equations along with other observations to estimate the expansion rate of the universe at different times and eventually determine its age. Another approach to determining the age of the universe involves observing exploding stars, specifically Type 1 supernovae. These supernovae act as standard candles since they have a known intrinsic brightness. By comparing their known luminosity to their observed luminosity, astronomers can determine their distance and, therefore, the expansion rate of the universe at different times. This method, used in the 1990s, played a crucial role in the discovery of dark energy, which is now essential to cosmological calculations. It is particularly useful for determining the Hubble constant, a measure of the expansion rate of the universe. Although not exactly constant, the Hubble constant is instrumental in charting the expansion of the universe since the Big Bang about 13.8 billion years ago. It has been observed that the universe has been expanding consistently. NASA has noted that the implications of this rate are significant. If the expansion is slowing down, it suggests the presence of an unknown force, perhaps dark matter, influencing this process. On the other hand, if the expansion rate is accelerating, it could indicate the presence and impact of dark energy speeding up the universe's growth. In January 2018, researchers found something interesting. Although some telescopes showed that the expansion rate of the universe changed depending on the place of observation, the Hubble Space Telescope measured a faster expansion in the nearby universe, while the Planck telescope measured a slightly lower expansion in the more distant parts of the universe. This discrepancy in measurement highlights the vast size of the universe and reminds us of the pioneering work of Edwin Hubble, who first proposed the expansion rate of the universe in 1929. Hubble's observations of distant galaxies revealed that they are moving away from us, demonstrating that the universe is expanding. This discovery was one of the foundations of modern cosmology. Now, considering the expansion of the universe independently of your local region, you would observe the same phenomenon at the same speed as the Hubble expansion rate. Initial calculations were based on limited data. However, with technological advances such as the Hubble and Gaia telescopes, we have been able to observe more variables and refine our measurements. Different telescopes use readings of the CMB to calculate the constant. Although this method has its limitations due to the availability of supernovae for distant observations, which limits our view of the universe, since the discovery of dark energy in the 20th century, researchers have been stumped by the inconsistencies between these two approaches to the age of the universe and its expansion rate.
As measurement technology becomes more accurate, smaller variations arise, driven by the development of more advanced systems. This progress, however, raises more questions than it provides definitive answers. Although the differences are minor, with just 10 to 20 million years separating the estimates, given that the universe is around 13.77 billion years old, it still warrants careful examination. One possible explanation for this discrepancy is the possibility of flaws in our measurements of the CMB. Despite being one of the most accurate measurements, it has been extensively tested since its launch in 2009 for validating its accuracy. Another perspective suggests a potential gap in our understanding of dark matter, raising the possibility that it may fluctuate over time and be linked to dark energy or some other unknown factor. This possibility has led to various experimental investigations. The accuracy of supernova measurements is also questioned, as the complexity of star explosions can introduce uncertainty into the models we use. Settling this uncertainty in supernova models could help resolve the disparity in measurements. This emergency in cosmology has been further exacerbated by the discovery of the James Webb Space Telescope. According to Neil deGrasse Tyson, the JWST found objects in the universe that challenge our current understanding. This means that our scientific understanding requires a complete update. However, the problem is that we have no idea where to begin to comprehend the extent of the scientific revolution. Let's take a look at the origins of the universe. Around 50 million years after the Big Bang, stars, black holes, and star clusters began to emerge, potentially even as soon as 50 to 100 million years later. However, these events should be relatively rare. What we don't know is how common galaxies evolved at later times, spanning events between 400 million years after the Big Bang. Ongoing JWST images reveal galaxies much more distant and, therefore, older than the standard cosmological model predicts. This disparity suggests that our model needs a major update. The discovery that the expanding universe relied on galaxies is a major development. JWST images show galaxies that formed much sooner than anticipated by current cosmological models, triggering a crisis in the field. This issue is related to galaxies and redshift, which is a common measurement in cosmology. According to the standard model, hydrogen began to appear 400,000 years after the Big Bang when protons and electrons combined, leading to hydrogen recombination. This changed the universe into a soup of hydrogen atoms, with some helium and residual background radiation. The gravity of the radiation then acted on small fluctuations in this hydrogen gas, slowly pulling them together to lead to the first stars. These early stars, made mostly of helium and hydrogen, engaged in nuclear fusion, creating heavier elements like carbon and nitrogen. These elements played a crucial role in galaxy formation by absorbing heat and emitting cooling photons, which facilitated the coalescence of gas into galaxies. The process of galaxy formation and evolution is complex and involves many stages. In the early universe, gas was primarily hydrogen, but as time went on, the gas became enriched with heavier elements produced in the cores of stars. This process led to the formation of galaxies that contain not just hydrogen and helium, but also carbon, oxygen, nitrogen, and other elements essential for life. The emergence of new discoveries, particularly those from the James Webb Space Telescope, has deeply influenced the way scientists view the universe. As researchers continue to explore deeper into space, the ability to observe galaxies and cosmic structures from earlier epochs of the universe challenges many previously held assumptions in cosmology. These observations are not just expanding the horizon of what we can see, but are also highlighting discrepancies between predictions made by cosmological models and the data obtained through advanced instruments. This growing body of evidence is forcing cosmologists to revisit old theories and rethink the mechanisms that govern the universe's structure and evolution. The implications of these new observations are vast. In particular, the JWST has provided us with images of galaxies that are significantly more mature and evolved than what was previously predicted for their redshift and age. These discoveries have prompted scientists to question the timeline of galaxy formation and the speed at which the universe's structures developed. Under the lambda CDM model, galaxies were thought to form slowly over billions of years. But the detection of galaxies forming as early as 400 million years after the Big Bang suggests that this process could have been much quicker. This unexpected finding indicates that the mechanisms behind galaxy formation may be more complex or efficient than previously thought. Moreover, the early appearance of such galaxies complicates the understanding of cosmic reionization. Reionization refers to the period in the universe's history when the first stars and galaxies emitted enough light to ionize the hydrogen gas that pervaded the early universe. The standard cosmological model places reionization between 400 million and 1 billion years after the Big Bang. The presence of mature galaxies at much earlier times suggests that reionization may have occurred earlier than expected, or that the process itself was more rapid and widespread than previously envisioned. These uncertainties could ultimately lead to a revision of our understanding of both the nature of dark energy and the cosmic timeline. Additionally, the increased ability to study distant galaxies is shedding light on the environments in which these early galaxies formed. Through detailed imaging and spectroscopy, scientists are beginning to understand the conditions of the intergalactic medium and how it influenced the development of galaxies. The interaction between galaxies and the surrounding gas, as well as the way these early structures clustered together, may have played a crucial role in the speed and nature of galaxy formation. By studying these interactions, cosmologists hope to unlock the mysteries surrounding the first few 100 million years of the universe's history. In another area of cosmological research, there has been growing interest in the relationship between dark matter and the formation of large-scale structures. While dark matter remains invisible and detectable only through its gravitational effects, its role in the universe's formation is crucial. The gravitational pull of dark matter is thought to have been responsible for guiding the formation of galaxies and galaxy clusters in the early universe. However, the presence of unexpectedly large and mature galaxies challenges the prevailing models of dark matter's influence. Some researchers suggest that dark matter may not behave in the uniform way we have long assumed and might be subject to fluctuations that could explain the accelerated formation of galaxies. Furthermore, the discovery of high redshift galaxies is also influencing the study of the cosmic microwave background, CMB. The CMB is a crucial relic of the Big Bang and provides a snapshot of the universe when it was just 380,000 years old.
The study of this radiation has already led to significant advancements in our understanding of the early universe. But the emergence of new galaxy populations that don't fit within the lambda CDM model raises questions about the accuracy of our interpretations of the CMB. Some scientists have proposed that the CMB may not be as indicative of the early universe as previously thought, or that there might be unknown factors influencing its signature. This would further complicate efforts to refine models of cosmic inflation and the subsequent evolution of the universe. In addition to theoretical questions, these developments prompt new technological challenges in astronomy. The JWST's ability to observe the faintest and most distant objects in the universe relies on cutting-edge instruments that are constantly pushing the boundaries of what is possible in terms of sensitivity and resolution. As more data pours in, scientists face the task of interpreting these findings and reconciling them with existing theories. This requires not only advancements in observational tools, but also improvements in computational methods to analyze vast amounts of data. The challenges of modeling these findings are significant but are essential for ensuring that cosmology continues to progress in an accurate and meaningful way. In summary, the field of cosmology is in the midst of a transformative period, largely driven by breakthroughs such as the James Webb Space Telescope. These discoveries are forcing a re-examination of long-standing models of the universe's history, from the formation of galaxies to the nature of dark energy and dark matter. With each new observation, the foundations of our understanding are tested, and cosmologists must adapt their theories to account for these novel findings. As the universe continues to reveal its secrets, the process of cosmological discovery will likely continue to evolve, leading to an even deeper understanding of the cosmos.